And please excuse me, the way my camera is set up on my laptop. I have two screens, so it's going to look like I'm looking above you all the time. But there's not much I can do about that. So firstly, I just wanted to say thanks for being here and the enthusiasm, and I appreciated everyone giving me some insight on people's background to help me tailor the course. And I know it's Friday afternoon, and I want us to feel comfortable I want us everybody to arrive in the room and feel comfortable with asking questions and speaking. So to get everybody going, I'd like everybody we'll go one by one, and you can give us your name, what your role is at uMngeni uThukela Water. Not sure which order that is, uThukela uMngeni Water. And if you were a fruit, what fruit would you be? So I'll just, I'll start to give an example, give you some time to think about fruits. I'm Julia Glenday. I have a background in hydrology and hydrological modeling. I do work for EcoSource at the moment, and I'm also a research associate at SEON and with Rhodes University IWR, Institute for Water Resources. And if I were a fruit, I would be a mango because I love them, and also because they turn lots of different colors, and so do I. I get sunburned very easily. Who wants to go next? We could go down. I can just call people. Or if anybody wants to popcorn, I'm just going to go in the order that I can see your name. So please just unmute your mic, and if you can, turn your camera on. Maybe everybody knows each other already, but Thobeka, are there a few Thobekas? Thobeka Sibande.
Okay, good afternoon, everyone. I'm Thobeka Sibande. I'm a graduate trainee and Catchment Management Department at uMngeni uThukela Water. I support the EI coordinator on the management of aquatic weeds in uMngeni in terms of operation, and I'm also responsible for the catchment assessment of Lower Thukela and Harding Weather, and then I assist where I'm required. If I was a fruit, I think I would be a pineapple because it looks hard outside, but it's soft inside, soft and sweet inside, because that's who I am. Thank you.
Thanks, Thobeka. Who's next that I can see? Sile.
Still on sound. Sorry. Hi, everyone. I'm Sivuisile Tanebe. I hope you can hear me. Sivuisile Tanebe with the Catchment Management Department at uMngeni. I work as an ecological infrastructure coordinator. And I think if I were fruit, I don't know, I think I'd be a nectarine, probably because they're nice, soft, and sweet and watery. And I think I'm as polite and warm and as it is. Thanks.
Nice. Gonna make us all one fruit now. Sharon.
That's it.
Hi, everyone. Am I audible?
Yes, we can hear you. Go for it.
Yes, my name is Sharon Bobo from uMngeni uThukela. I'm a graduate trainee. And if I were a fruit, I think I'd be a banana because it's very simple. I'm a very simple human being. I like simple things. What was the other question?
It was just your name, your role at uMngeni Water, and the fruit.
Okay, that's just about it.
Thanks. Nombuso.
Good day, everyone. I'm Nombuso Gongo. I'm with uNtando Ndlazi. Apologies, we're on the road on our way to the office. So yeah, we're joining through a cell phone. Okay, we are EI coordinators under catchment. Fruits in done. Okay. I'm not sure what fruit we're gonna choose.
What's your favorite one to eat?
Is tomato a fruit? I think it's a fruit.
It is actually, yeah.
Yeah. So
Technically.
yeah, team tomato on this side. So yeah, thanks.
Nice. Danele, you guys together, hey, the car.
No,
Sorry?
Usanele at the office.
Oh, okay. No, Nombuso, is there somebody else with you?
Yes, I'm Ndlazi.
Oh, okay.
Yeah, he's busy driving, so yeah.
Okay.
Yeah.
He's with you on the tomato train.
Yes, yeah,
Okay.
tomato.
Thanks. Sorry, Sanele. Go for it.
Good day, everyone. My name is Usanele Vilagazi, also from the same Department of Catchment Management under uMngeni uThukela Water. I also serve as an ecological infrastructure coordinator. With regards to the fruit, I'd say I'd be a pineapple. Sweet, but can hurt you if not delicately handled. Thank you.
Thanks. We have to do something fun on Friday afternoon, so we're doing things. Zamani.
Hi, my name is Zamani Zulu. I'm a graduate trainee at uMngeni Water under catchment management. If I were a fruit, I think I'll be a lemon. You can enjoy it with many things. You can put it in your tea, your porridge. Yeah.
Tobeka Tolo. Please, excuse me, I'm gonna pronounce names incorrectly and I'm gonna try and get better.
Hi everyone.
Hi, Tobeka.
Tobeka Tolo, and I'm a graduate trainee under Catchment Management Department at uThukela Water. And well, if I were a fruit, I'd probably be a nectarine as well. Well, because I like them.
Nice. And Tombi.
Good afternoon, everyone. My name is uNtombi Hadebe. I'm also from Catchment Management at uMngeni uThukela Water. I'm a graduate trainee. If I were to be a fruit, I think I'll pick a green apple because it's a little bit sour and I'll always be on stock. Thank you. In stock.
Thanks. Toko's easy. Easy.
Good afternoon, can you hear me?
Sorry, we're struggling to hear you, or I'm struggling to hear you.
Can you hear me now?
Yes, I can hear you now.
Oh, okay. Good afternoon, colleagues. My name is uThukela. I'm also a graduate trainee at under catchment management at uMngeni uThukela Water. My role is I'm responsible for climate change initiatives and I support Untando for the projects that they do with EcoSource, and I'm also responsible for coordinating catchment assessments, and we are currently conducting one at Ikopo. I'm with three of my colleagues, Unwabi Sadlamini, Umamtanda, and Uzingisa Gono. They'll respond afterwards. If I were to be a fruit, I think I'd be a cucumber, very versatile. Thank you.
Maybe the others on your call can introduce themselves just because I can't see the names on the list. So please go ahead.
Singisa is an orange.
Hi.
Why?
It's my favorite fruit.
It's Nwabisa Dlamini here. My favorite one is banana because it's soft. I'm also soft, but sometimes I get hard as the the outside of the banana.
Thanks.
Passion fruit, hard on the outside, mushy on the inside. Thank you.
Thank you. That's all from us.
Thanks, team. Sane Mtube.
Good day, everyone. My name is Sanim Mube. I'm also a graduate trainee under Catchment Management Department. If I were to be a fruit, I would be a watermelon because it's very refreshing. Thank you.
Nice. Thanks, everyone. That's everybody I can see, I think, on my list. Did I miss anybody? Oh, Marofa. Did I miss you, Marofa? Introduce yourself. Did I miss anyone?
Roka, you need to introduce yourself and then tell us what fruit you are. Okay, I'm not quite sure what's happening here.
Able to unmute. Marofa, are you there? Are you struggling to unmute?
Hi guys.
Hi.
Sorry, I'm a bit late. I'm actually on my mobile. I hope you can. I'm audible.
Oh, shame. Thanks for joining.
Oh, yes, thanks, Dr. Lendi. I'm just going to mute and listen.
Okay, that's fine.
Thank you.
Great. Well, thanks everyone. Good to meet our fruit salad, and we're gonna start going through the materials. So Jason gave us some background on why we're here right now and why we're doing this training. In a previous, like an earlier stage of this project, I helped to set up a model of several of the catchments that feed to uMngeni water managed reservoirs. And the goals of setting up that model in SWAT were to look at the hydrology and the water quality, and particularly look at point versus non-point sources of water pollution. And then ideally, hopefully that model could be used to forecast some water quality issues given weather forecasts and what water quality issues feeding into the reservoirs. So as Jason mentioned, we linked the idea is to link the SWAT model with some of the more specific reservoir models he was building in Mike software, and then potentially to be able to use it for evaluating management scenarios of various water quality sources, water pollutant sources. Where we got to with that model, it was producing reasonable stream flow outputs. The water quality outputs were quite mixed. Some were looking okay, and some where we were having issues, and I think part of it is because of some of the data inputs we were using, and we'll as we go through this training, we'll see together how we can improve that and how can it be improved over time with data that people have access to about different sources and about the hydrology as well. So now, in this current iteration of the project, we're going to update that model. So the original model was built in ArcSWAT software, which is a software. The SWAT model has had many editions. It's been going for over 45 years. So there's like lots of different versions of it out there. But the most recent one and the one that's going to be supported going forward is SWAT Plus. And so that's what I'm going to be doing the training with. And we're going to move the model over the previous existing model, move it over to SWAT Plus and improve it with updated data. And then the other thing is to train you guys all to continue to use it and update it going forward. And the more people who know how to work with it in one capacity or another, the better, or at least understand what it's doing, what it's not doing, what kind of data it needs. I see everyone's in different departments. They're going to have different roles or uses for it. And there'll be some discussion of like who's going to be running it and where it's going to sit on everybody's computers and that kind of stuff. But for now, let's focus on understanding it to start with. But that's why we're all here. And oops, I went backwards. So the goals of the training is for everybody to at least understand how the SWAT Plus model is estimating water flows and water quality, and to know how to run the SWAT Plus model that we build of the uMngeni uThukela catchment areas, and to analyze the outputs that it produces. And then to know how to modify that model. So I'll be working on the existing, the first run of the setup, but then the idea is that people across your departments will be able to know how to add, change some of the inputs, change new data, and use it to look at future scenarios. So it can change properties of the land cover or those kinds of things, climate inputs. I noticed some people are on climate change, and use it that way. But there's lots of ways one could use it depending on how well it's performing. So as an overview of the entire training over the next months, we're going to spread it out because there's a lot to cover. And I feel like when you go to these short trainings where it's all day, every day for 5 days or something, your brain kind of can't take everything in. And it's nice to have some space to think about things in between. So over the sessions, I'm going to go into how hydrological and water quality modeling works more broadly, not just for SWAT Plus, but it all applies to the SWAT Plus model. And then how the software works, the SWAT Plus model software in particular, and then how we're going to build the model for your catchment areas. The decisions that I've made to build the first cut model and how I've prepared the input data, and then how you could prepare new data and change that if you wanted to. And then what the output data looks like and how to get at it through different formatting, how to calibrate and improve the model over time, and the scenario modeling. So it's quite a lot of stuff. That's why I think it'll be nice to spread it out. In terms of logistics of the course, so there's going to be lecturing like I'm doing now, and then some practical material. So like tutorials, and some of that we're always going to start doing it in the sessions together, but it takes different people different amounts of time because of their computers and it's nice to be able to go through it on your own time as well. So there will be some you can go through things on your own time as well. Then there'll be recordings of the sessions. So the session's being recorded, and then what I'll do is I'll edit down. There's going to be pauses and ums and things that we don't need to keep in a recording. So I'll edit down versions of the recordings as well, so that you can use them later for going back to if you need to. And as I go through material, even before we're doing the tutorial stuff, please, if there's like a critical question, like I've said something that really didn't make sense, please just unmute yourself and ask. If it's something you think that it can wait, you can put it in the chat. I've put in pauses throughout the presentations for myself to check the chat, and also for people to ask questions as well. But do feel free to interrupt me if something is really confusing or there's something critical to interrupt me about. In terms of emailing me in between our sessions, like about issues with the practicals or other questions, you're welcome to do that. I'm going to commit to only looking at emails about this on Wednesday mornings, because I'm managing a few projects and I can't commit to, so just so you know that. So I will look on Wednesday mornings, and if you can put SWAT Plus in the subject line of the email, then I can pick them all out and reply in as much as I can. I think like nowadays there's so many different ways to teach yourself about any given subject. So I'm going to cover as much as I can, but there's so much, it's a huge field to go into, and different people are going to go into different things in different depths. So there's a lot of manuals and material out there on the SWAT Plus model and on hydrological modeling in general. There's lots of YouTube videos as well. There's AI lots of AI help that has access to all of that material as well, so can synthesize things in the way that you want it to. But I have found sometimes it gives you strange answers, so you just have to sense check the answers that it gives you as well. In terms of going through tutorials and that I'm very happy for everyone to work in groups or not as you like, and to ask everybody else when you're working on some of the tutorials afterwards as well. So for today, we're doing this course intro, starting to get to know why we're here, who everyone is. At least for me, I think most of you probably know each other, but maybe not. It's a big organization, I realized. And I'm going to do some hydrological modeling theory overview, and then some introduction to SWAT plus, the particular model we're using, the structure of it, and how it represents the hydrology. Talk more about water quality, particularly in the next session, and then how the software itself is structured. And we can start working through a tutorial that introduces you to the software itself. So that's what I'm hoping to get through today. I know 3 hours is quite a long time, so I am going to pause for 5 minutes every hour. When I get to, I'll try and see what section I'm getting to and take a pause so you can run and get some tea or use the bathroom or something without missing too much. So another thing I want to say before I start getting into material is that modeling is really a team sport. There's a lot of elements in it, as we're going to get into, and it is something that different people on this call or on this training are going to bring different skills to help it happen. There's elements of working with time series data, like rainfall data and streamflow data and water quality data. There's spatial data, like, you know, maps of soils and land cover and stuff. And then there's working out software and why it's giving you an error and that kind of elements. There's understanding how the hydrology works, understanding how the water quality works. When I say modeling theory, there's like how do you check if it's doing the right things? And then the water quality management, understanding what kind of outputs do we need to make decisions in the first place, and some of the statistics and synthesis. And then there's communication of the outputs and communication between people who are helping you find the inputs. So there's a lot of skills to be brought to bear, and you can't expect everyone, like any one person, to have all the skills. So that's why it's great that there's so many people at this training, and we can get together and hopefully make a really helpful model. So now I'm going to start getting into hydrological modeling theory. I'm actually going to turn my camera off because I think it might be distracting. Okay, there we go. So I'm going to step way back because I think it does help to sort of prime ourselves to what a model even is and why we make models. And I'm not going to spend too long on the very basic stuff, but just to get everybody on the same page. So what is it? What is a model anyway, and why do we make them? It's something, either a physical object or a diagram or a set of equations that provides a simplified representation of a more complex or a larger object or system in the real world. And so we make models for lots of different reasons, and the reason that we make the model influences how we make it and what elements are included and what elements aren't. And so the example I like a lot is a map, and it's kind of a recreation of the world or a piece of the world that helps us get around. And depending on what we want to know, it depends what we want to include. So you can have a globe, but then that doesn't zoom in well enough for, you know, driving from A to B. But it does represent the fact that the Earth is round, for example, and you can see where things are in relation to each other and the shape is accurate. But then you can't put it on a wall or put it on a phone screen. So then we flatten it. And when we flatten it, we start making assumptions about how to flatten it, and the shapes of things change. And then there's also, you know, what scale and detail do we want to go into and what do we want to show? And so for getting around or driving around, it might actually help to have the map on the bottom right where it's much more simplified and I can just see the main roads and the turns. all the detail in the image on the left might actually be a bit confusing, and I don't know which alleyway is actually a street I could drive on or walk on, for example. So there's lots of different ways of flattening the earth and what details to include. And it depends on the reason why we make the model to help us. So what is then a hydrological model? It's a representation of how water moves in an area. And that area can be a plot, it could be a hill slope, it could be a catchment. And generally we're working with catchments, but you can do smaller pieces if you want. And it provides a description and a prediction of the water balance of that area. So I'm going to talk about what the water balance is. And the idea of a model and how the calculations work is it tries to close that water balance. So the equations balance. I'll show you what that means. You can think of it like a bank balance. You have your inputs and you have your outputs. So your inputs minus your outputs equals your storage. Your change in storage, I should say. So if you have your income and then what you spend, and then what's left is the amount in the bank account. And it can be going up, the amount of change in the storage. So is it going up or is it going down? So when we think about that with water, we've got, what are the inputs here for a catchment? We've got rainfall. And then if you're using an area that's not a full catchment from the headwaters all the way down, then you could have stream flow in. And you can have groundwater in from the edges, depending on what the groundwater aquifer looks like. But generally, it's rainfall. And you can have artificial transfers of water in, as I'm sure you work with as well in your systems. But the biggest one is generally rainfall. And then the second biggest is often these transfers that we make between catchments. So what are your outputs? Are then evapotranspiration and then stream flow out. And you can also have groundwater flow out that flows out below where your stream flows out. So it doesn't appear in the stream flow. It's flowing in the rock below, and it can leave your delineated catchment area, depending on how the aquifers in your area work. And then you can have water transfers out, leaving the catchment area. And so what storages are we talking about that can then change? Oops, I went the wrong way. There we go. Storage. So for the storages that can change, you have your soil moisture, you have your groundwater storage, and then you have storage in surface water. So there is a bit of storage in the stream channel itself, and then ponding on the land surface, wetlands, dams, reservoirs, are all the surface water storages. So those can go up and down. If the inputs are greater than the outputs, then you will increase your storage. If the outputs are greater than the inputs, your storages will decrease, and they all have links to one another. So this is all pretty common sense stuff, but this is how numerical hydrological models are built to balance these equations. And so then what I'm going to do now is we're going to rearrange this equation a bit to get to the way that we usually use it in a hydrological model. So you have your inputs to the catchment, your rainfall, and then that rainfall, some of it's going to run off and some of it's going to add to your soil storage and your groundwater storage. And some of it's that will determine what kind of outputs you can get in terms of stream flow and ET, what gets stored in the soil, what runs off the top, what goes into the groundwater. So that's showing it that way. So your inputs minus what gets added to storage versus what is going to give what outflows you have. And then if you start breaking down your outflows, your main outflows are usually evapotranspiration and stream flow out. So if we rewrite the equation here, you have rainfall minus any change in your soil moisture or your groundwater and your surface water storage is going to give you stream flow plus evapotranspiration. And usually what we want to get to is your stream flow. So if I move evapotranspiration to the other side of the equation, usually what you do is rainfall minus evapotranspiration minus any change in your storage, more water being added to the soil moisture that stays there, in the groundwater that stays there, surface water that stays there in your time period is going to give the stream flow that you have in your time period. So this is what our models are calculating every time step. So every day or every month or every hour if you want. It will run through this equation. So I hope this makes sense to everyone. It is pretty basic stuff, but we don't always think through it, but it has impact for, as you'll see later, for how these models work. So, oops. Yeah, so then we have to think about what parts of this equation do we have actual data for, and then what parts are the unknowns that we want to solve for. So typically we're wanting to solve for stream flow, but there are other unknowns that we have to solve for in our modeling. And what are some of the processes that determine the pathway between the inputs and the storages and the outputs? And then how do we describe these with mathematical equations? And that's what makes up a hydrological model. So when I say, sorry, pardon me, I'm going back a sec. How do we describe these processes with mathematical equations? When I say these processes and the processes that determine the pathway of water, you can see in this diagram on the left, you've got rainfall and it hits the land surface. And it hits the vegetation surface. Firstly, it can get stuck on the leaves, that's canopy interception, or it can fall to the soil. And then if it falls on the soil, it can either run off or it can infiltrate into the soil. So part of it's going to do one, part of it's going to do the other. And then once it's in the soil, it could flow laterally, it could percolate down and recharge the groundwater, or it can get used in evapotranspiration by the plants or soil surface evapotranspiration. So all these processes are controlling the relationship between the inputs and the outputs and the storages. And then it could go down to the aquifer, and then it can either, it can sit there, it can flow out to the stream, or it can go further down, or it can flow out of the catchment area completely, depending on the nature of the aquifer. So we describe all these processes with equations, and then we get our hydrological model. So we've got inputs are the things that we know we have some data on. And then we have the equations between to get to the outputs, which are the things we don't know. So we need to have some information on rainfall and evaporative demand. And that means like the drive for plants to use water and for the water to evaporate out of the soil. And we have different catchment property descriptors that are going to describe those storages, the soil and the vegetation canopy and the vegetation that's there and aquifer that's there. That'll go into your equations that are going to give you your stream flow and your evapotranspiration, the soil moisture storage, groundwater storage. Those are all outputs of the model. So I'm going to pause here for a second. Is this all making sense to some degree? Anybody got some thumbs up? It's
Yes.
quite basic, but I want to get us in the same language and headspace before I go into more details. Great. So if it's not making sense to you, these things are going to come back over and over in different formats. So don't worry about it, but feel free to ask questions as I go. So now we have this numerical model, be it SWAT or ACRU or Pitman or other models. They all have some components. So there's the structure of the model, and that's our modeled units and how they are connected. So we're going to talk about what that means just now. So like areas of land and how we break it up. How do we break up the aquifers into different units? Do we break them up, or is it just one sort of bucket? You have your river reaches, water bodies. So that's the structure of the model. How do we break up space into separate units, or do we keep it all as one unit, and what flows between what? Then you have your algorithms, which are equations and rules that determine how the water moves between the units. And so what that really means is these estimations of processes. Do you have infiltration? Do you have evapotranspiration, groundwater recharge, groundwater flow, overland flow? These kinds of things are described with equations. And parameters are values that are used in these equations or these algorithms that adjust for specific cases and settings. So like properties of the land cover and properties of the soil, like what's the porosity of the soil is going to determine what your infiltration will look like. And then you have input variables, or sometimes people say input data. These are like time varying inputs to the system. So rain, the evaporative demand of the atmosphere, and I'll get into that a bit more. And your external water inputs, pumping, transfers, that kind of stuff that changes day to day or month to month, hour to hour, and that you would need to feed into the model to do your predictions and to do the calculations. And then your output variables, so those are things like stream flow, evapotranspiration, groundwater storage, that the model actually calculates by using the algorithms. So I'm going to go through some of these bits. So you have your model domain, or is the whole area that you're modeling. So in our case, it's a set of a few catchments. But as I said, you can equally build models of smaller, just plots of land that people also do, or a hill slope or a floodplain area. If you do build a model that is for a smaller area than like a closed catchment that goes from the mountaintops downwards, then you need to have the boundary condition inflows from the outside. So any flow over the edge of your model area going inwards would need to be specified. If we then go to within your whole model domain, there's something called discretization, or some people also say delineation. You might have heard this when a number of people said they have worked with some models before in coursework a lot. Some more recently, some a long time ago, but you might have heard the term delineation as well for subcatchments and catchments. So what I mean by discretization is breaking things up into units, into the modeled units that we do calculations with. So we break up space, we break up the catchment area into modeled spatial units. Those can be subcatchments, areas of certain land cover types, and we break them up into buckets essentially that we can model. And we also break up vertical space. So we can break up the soils into different layers, and we can break up the rock material underneath the soil into different aquifer layers within our spatial units. And then we also break up time into time steps. So often our models these days are daily or less. Older models were monthly because the data wasn't as good, but we'll talk about that. And then we break up how we look at how individual processes are calculated in a way that relates to how we've broken up space and how we've broken up time. So it all sounds really conceptual, but it'll make sense as we get into it. But they're all linked. So if I model a tiny, tiny amount of space, the water is going to move across that space very quickly. So my time step needs to be a bit bigger to make sense. And then if my smallest modeled unit is quite large, the water can move across it very slowly. It doesn't make sense for me to model it at a 1 second time step because the water is not going to go anywhere. It's not going to cross my unit in 1 second kind of thing. I'd better do a day or a month. So these things are all linked when we make a model. So what do I mean with spatial units? And we're going to get to what SWAT does in particular for this soon. But modeled spatial units are the units for which the water, the inflows and the outflows and the storages are calculated. So I hope this diagram kind of helps a bit. Like you have a chunk of land, it's got vegetation, it's got some soil, it's got an aquifer. You could model that as a unit, and then a neighboring piece and a neighboring piece could be modeled separately, or you group them. And so there's different ways of dividing up a catchment area into different units. And I'm sure you've seen subcatchments before, but some models break things up into grids, grid squares, and there's reasons for doing that. And then once you start breaking things into subunits, like these spatial units, you have to define how things are linked. So what flows into what are the neighbors, what's upslope versus downslope, what's connected directly to the stream, what land has to flow across other land before it reaches a stream. And then you have your vertical connections, like does the soil recharge the groundwater, or is there some hard layer in between that stops the water moving downwards? So you have your units and you have the linkages between them. So there's different types of models that approach this differently. You could lump the entire catchment as one unit, and some people do that, and it's helpful in some cases, but we generally are working with something more in the middle. So semi-distributed models break land up into subcatchments and then further into hydrological response units, which I'm going to come to what those are in a sec. And then other models use a grid cell approach where they break up the land area into equally sized grid cells. And they do these calculations of rainfall, evapotranspiration, infiltration, percolation, groundwater recharge, for every, either at the subcatchment scale, at the HRU scale, or at the grid cell scale, the model is calculating these things. So like as a visual example, there's a distributed model. This is where everything is represented with grid cells and going downwards into the aquifer as well. You could do 3D cubes of aquifer material. Oops, okay. Skip forward and go back. So an example of a model that does that, a modeling software that does that is Mike Shee. And you have to track the connections between every cell and all of its neighbors. So if your grid cells are small, it gets very computationally heavy. You can use really large grid cells to make things lighter. So there are these hydrological models now of the entire world that use remote sensing products for their inputs. And they have very big grid cell sizes, like several kilometers sometimes. So that's like an application of a gridded model where they've tried to keep, you can balance the computational heavy nature of it by making the grid cells larger, for example. And it lets you get inputs and outputs at the level of your grid cell. Then another approach is what I called semi-distributed, and you can use subcatchments for units, and you could model the processes for entire subcatchments. And those of you who have used the Pittman model, which is what Department of Water often used for the water resources studies of 2012 and before, you might know WR 2012 or WRSM or SPATSIM, those models. And then earlier versions of ACRU 3 used a subcatchment approach. And that has straightforward linkages between subcatchments, and it's very quick to do the computations generally. There are some limitations of it, is that you end up lumping land cover types within a subcatchment for both your inputs and your outputs. And a lot of times we want to know the impacts of specific land cover types. And so models then added some subunits, like the WRSM and SPATSIM have subunits for alien vegetation and irrigated areas specifically. But there's another way, the other approach to starting to separate out land cover so that we can look at its impacts more explicitly is using something, if you're not using a grid, is using something called an HRU. And people who have worked with the ACRU model before the more recent versions of it will likely have come across an HRU before, and the SWAT model uses HRUs. And there's hydrological response unit. And that's an area of land that's considered to be hydrologically homogeneous. So it has similar vegetation, soil, slope, and topographic position throughout a chunk of land. So it doesn't have to be a contiguous area. You might have you might lump all the areas of non-irrigated maize on clayey soil within your subcatchment. And there might be different patches of that throughout your subcatchment, but you model that all as one chunk. So you would work out where all of those areas are and lump them into a total area of like maize on a flat slope and a clayey soil. That might be a bad example, but you get the idea. You'd group it so it's not always, you come up with these groupings within your subcatchment of land areas that you think are going to respond similarly if they get the same amount of rainfall. And so I've kind of shown that diagrammatically for another catchment that I've worked on. So you see there's a land cover map here that has the different light greens. This is fynbos and forest. This is a Western Cape area. There's the red is wattles and pines, the alien vegetation, and then you've got irrigated fields of the bright green. And then I broke it up, the picture, the simplified, the way that's being represented in the model further down. We've got these 3 subcatchments, and you've summed up all the area that is forest and all the area that is an irrigated field, all the area that's an orchard within that subcatchment, all the area that's wattle, pine, and each one of those is getting represented with a model unit. And now you'll notice in the subcatchment, sometimes there's 2 red units, even though it's in the same subcatchment. And the reason those have been separated in this example is that I wanted to give different parts of it different amounts of rainfall. So there was a north-facing slope and a south-facing slope that got very different rainfall. This is a mountain area. So then you separate areas, even though it has the same land cover, you separate it into 2 HRUs, the ones that get the high rainfall and the ones that get the low rainfall, for example. So we look at how we divide our land based on our specific catchment. So as I go through these things, we want to start in the back of your head, kind of thinking, how would you do this for the areas that you work in? But does everybody understand what an HRU is, more or less, at this point? Feel free to ask anything, or if you want me to say it in a different way, I can't. Because this is quite a key concept. I'm getting lots of thumbs up. Cool. We can come back to it if we need to. So the next thing we do is, once we've broken up our catchment into these units, these HRUs, so these shapies I've got here in the bottom left, we have to decide how they're going to get linked, because each one of them is going to produce runoff, like overland runoff and soil runoff and groundwater runoff potentially. So then you have to say, how is that water going to flow in the landscape? So this diagram is showing a delineation of, like, what I call landscape units. So you've got canyon floors are the dark blue, you've got cliffs are in gray, you've got plateaus and hill slopes that have been mapped out for, this is just a little subcatchment example based on topography. And you have HRUs for them. And then you have to say, how is that water that leaves each one gonna reach a stream? And a typical way of doing it was parallel routing, where each HRU, you just calculate the runoff for each one and you add them all up into the stream. But in reality, water does flow from one area to the next area to the next area. So like from the plateau to the hill slope, maybe off a cliff, and then to the valley bottom, and then into the stream. So you can choose, different models handle this differently, and we'll get into how SWAT does it. So parallel routing, what we call parallel routing, is all the HRUs just get linked directly to the stream. They don't feed water into one another. What that means is that the arrangement of them in space is not really represented in the model. What you're representing is how much there is of different land covers, but we're not representing if there is a buffer around the stream channel, for example, that like if you've got a wetland or something that might stop some of your pollutants or slow down some of the flows and stuff, that wouldn't get represented here. Some impacts of the wetland would be there, but the fact that the water from the top of the hill flows through the wetland before it gets to the stream would not be represented, for example. If you had series routing, you do represent the spatial arrangement of your land covers or your HRUs. And so that's nice, but it's much more complicated mathematically to do that. So it's been a more recent thing in HRU style models to do that. There's some medium ways of doing it in both ACRU and SWAT, for example. Because people have realized you kind of need to do it for certain cases. In some cases, you can get away with not doing it. So just something to keep in mind. When we break up space, we have to think about how we link the space back together again to get our entire catchment output and what reaches the stream. We're also going to divide things vertically. You could treat all the soil and the rock and stuff as one chunk. It's very typical to break up break the soil and the groundwater, the unsaturated part of the soil and the saturated rock and the into different aquifer properties, the saturated portion of the depth. And then some models get more and more fancy, and SWAT allows you to do up to 12 layers of soil if you want to. You can just do 1, you can do 2, you can do up to 12. And then there's an aquifer, the groundwater below. And you have to look at where the roots are. So there's different ways of handling how water flows vertically as well. And then, as I mentioned, like when you break up space into HRUs and subcatchments, we then have to look at how they link back together again. Aquifers, like groundwater storage, it's not broken by the land, like we're breaking things by land cover types, for example, or soil types, but the rock underneath is not broken into chunks in the same way. You'll have a larger area of one geology type or another. And so what models often do is that they break up the surface and the shallow subsurface, like down to soil, into these HRUs. But below that, you have bigger aquifer storages that are treated like buckets underneath your smaller HRUs. So that's what SWAT does. There are versions of ACRU that do that. The original ACRU kept one, like an aquifer unit for every HRU, which is not quite the way that aquifers really work. And so the groundwater representation was a bit more questionable there, but you could make it work. But what other tools do allow you to do, like Mike and SWAT, and they have, you can lump the groundwater in different ways, sort of underneath your layer of HRUs. So the diagram on the right is showing more what that looks like. You have your smaller either grid cells if you want, or HRUs in the case of SWAT, that go down through the root zone, and then below you have these bigger buckets for groundwater movement. And then another element of this, we've been talking about how we break up the land surface, and we've been talking about how we break up the soils and a bit the groundwater, but then all of these are also connected into a flow network of channels and water bodies and transfer, that you might have a transfer system. So showing this diagrammatically, and then an example catchment there on the left with some water bodies in it. And the channels themselves can be quite complicated. There can be things going on, they can overflow, there can be feedbacks with aquifers and stuff, and different models represent that to different degrees or simplify that to different degrees. So you'll have these channel units, and you look at which land units are connecting to those channel units and how they are connected to how each channel is connected to one another. So you have your streams building into bigger rivers, and which processes in the river channels are represented in the models can vary a lot, and we'll go into what SWAT does for that. And channels can act as just like a simple pipe, so everything that goes in just comes out the other side. Or you can have things happening as it moves along the stream. And then you have water body units, so your dams and your reservoirs, and maybe like small farm dams and wetlands and other places where water gets stored, surface water gets stored, that behave differently than other parts of the land. And we'll go into what SWAT does for that. So that's something that's in a hydrological model you have to deal with, and different models do it differently. And you look at what connections there are between the land units and the channel units and the water body units. So I'm going to take a break at this point. This is where I've gone through a lot of how the basics of like a model structure for a hydrological model. I realize we're almost 2 o'clock. So I'm going to take a break for questions, and then I'm going to let us take a 5-minute break to stretch, use the bathroom, get it running, get a cup of tea or what you need. But before that, does anybody have any questions on what I've just covered? Am I doing all right? So let's take a little break until, what is it now? On my clock says it's 1:58. So let's do 5 minutes. I don't want to do too much more than that because we'll run out of time. We will have another break. And we can feedback at the end whether you guys want to do 2 5 minutes or 1 10-minute, but let's try this today. So I'll see everyone back at 3 minutes past 2. Please take a stretch. Thanks. So Becca, I see your hand up.
Oh, yes. I know you answered this. I mean, you talked about this in terms of separating this in units, because I understand in surface part, you can separate it by looking at the vegetations or soils. But then in terms of groundwater, okay, this is a slide that I'll want you to repeat it because I didn't understand it.
Cool, thanks. No, it's a good question. And guys, don't be shy. Everybody, like, I'm happy to try and explain things differently and improve the way we say it. So yeah, with this, like you would often these models some models treat the groundwater as this grid. Let me go back to this one. So groundwater models get super fancy. Oops. And treat it as this like 3D grid. I come to the Mike Shi one. Oops. Yeah, like this 3D grid thing where every grid cell is this is a chunk, like a cube of rock, and it works out how much water is in each cube and it flows between them. But when you're doing an HRU style model, it tends to be like a bucket for a whole subcatchment often, for the groundwater. Or if your subcatchment has 2 big geological types, or 2, it depends. You'll have to have some sort of understanding of what the aquifers look like in your area. So you might have like an area of fractured granite or sandstone or something. And then there's part like a lower floodplain part of the catchment might have like a really thick deposit of sand that is saturated. There's a lot of groundwater there further down. So you might call those 2 things, there might be a fractured rock aquifer and there might be a sandy aquifer close to the river in the floodplain, like the lowlands. So you might want to make those 2 different like groundwater, I'm calling them buckets. They're not exactly buckets because they have different rules for flowing in and out, but like here you might have the upper areas might have a fractured rock aquifer, and then these lower areas closer to the stream might have like a sandy aquifer. So you treat those as 2 different buckets within your subcatchment, and you would know which HRUs lie on top of which one. So you might separate them. And we'll get into how SWAT helps you to do that, but it does require a bit of knowledge about the geology in the area, and the hydrogeology, I should say. I hope that helps.
Okay, it does help. Thank you.
Welcome. No, thanks for the question. I'm gonna let us go. Yeah, let the break go until. Give it a little more time. Let's take a break from now, actually, until what will be like 8 past 2. I'll start again. Hi, everybody. I hope people are back in the room, stretched a little bit. I see a few thumbs up. I'd love to wait for everyone, but there are quite a few of us, so I am just going to keep going. I'm going to start the recording again, and then, because at least it's recorded, people who got back late can catch up. So we're gonna get going. So what we just covered in the previous session before the break was we started looking what are some of the nuts and bolts and the guts of a numerical hydrological model. So we've got the structure. So that's how we break up a catchment area into areas of land and aquifers and reaches of river and water bodies. And all of those need to get connected. And then we've got our equations, which I'm going to go into a little bit now. So these are the rules that we use to describe how water moves between one unit and another. And what that really means is how we're estimating the processes of things like infiltration, moving into the soil, ET moving out of the soil, groundwater recharge, so moving downwards into the groundwater, those kinds of things, overland flow, moving over the surface from one land unit to another or into the river channel. So those are all going to be described by equations. And those equations have parameter values. And I'll go into more about that just now. And those are like adjusting for things like properties of the land cover, properties of the soil, or properties of the rock that describe how that movement happens between the different units. And then you have the input variables like rainfall and your output variables like stream flow. So I'm gonna get into the mathy bit. Just some terms, we don't have to get too, what's nice about modeling is you don't have to understand all the details of the math, but what you do need to understand at some point is what the different parameters are in the particular model you're working with. So in SWAT in this case, what the parameter values are, what they mean, and how we pick the values for them, you know, based on the land cover types, based on the soils, based on the slopes and that kind of stuff. But you don't have to understand all the equation, like the forms of all the equations. You just have to you have to understand what the parameter values mean, like the porosity of the soil or those kinds of things. But in terms of getting ourselves on the same page, somebody's want to ask a question? No? I'll keep going. But do feel free to jump in if you need to or you want to. So to get on the same page with some of the language, in terms of variables, algorithms and variables and parameters. So the algorithms are just the equations, and sometimes they're equations, sometimes they're more like if-then, like yes-no statements for a threshold, like if the soil reaches saturation, then everything else, any more rainfall after that is just going to flow over the top because it's already full. So it's kind of more of an if-then statement sometimes, and sometimes it's an equation. So this is just an equation of a line as an example. So everybody should have seen that to some degree. So you have your input variable is your X, your output variable is your Y. You want to predict the Y value. You have input, so let's say it's rainfall or something, and then your A and your B values are parameter values. So if I'm saying I'm working with time series data, X with a sub T, that's like, let's say that's rainfall for today. And so the T is a time step. So you can have the first time step, the next time step, it's individual days. And then if Y was the output was stream flow, you'd have the stream flow on day 1, day 2, day 3. And A and B are values that are not changing by day. So they're parameter values. So they are things that help describe how the input is related to the output. So if this is a linear relationship between the input of X and the output of Y, the A, which is the slope of the line in this case, and B is the intercept of the line in this case, in a linear relationship are parameters in a linear equation. So to say that a bit differently, variables or your input data and your output data are these inherently changing things in the system. So rainfall can be different every day, every hour, temperature, stream flow. And And then your algorithm is the equation that links your input variables to your output variables. But essentially it's describing the process of infiltration, the process of percolation, the process of runoff with an equation. And sometimes they're threshold, sometimes it's a linear relationship, sometimes it's an exponential relationship, sometimes there's a threshold, as I say, like the groundwater is full now, so everything else is going to become runoff. Or the soil is full now, for example. And then what is the relative influence of these different parameters on the output and the different inputs on the output? So there's the inputs are also like the evaporative demand and the rainfall are both impacting the stream flow. So you have the equations that describe that whole chain. And then the parameters are then these values that help describe that are part of that equation. And it's like an oversimplification of the world. So parameter values are often assumed not to change over time, but they actually do change over time, like land cover changes. And land cover can have a seasonality, like the properties of the land cover can have a seasonality to it, like crops and things. So sometimes we vary it monthly, or you can vary it different years. So they're not always unchanging, but they're not changing in the way that rainfall is changing. It's a false separation really between variables and parameters in a way, but the parameters are assumed to be more stable than the variables, just to make the math doable, to get it to an output. Because as I say, it's a simplification that we use to do some like management with, but there's always assumptions. So we assume that the soil properties don't change hugely from one day to the next. And slope doesn't change over a short enough time period for us to vary it in our model, those kinds of things. So those, we call them parameters because they're fairly stable. And then calibration, we're going to come back to calibration a few times, but I'm just going to introduce the idea, is that we have to pick what these parameter values are. We have to give we have to assign a soil type with a porosity or an infiltration rate. And we have to assign a vegetation type with a maximum evapotranspiration rate, or those kinds of things, or parameter values that we're assigning when we build our model. But we often don't know exactly what they are. We know they're in the range, or we know like the sandy soil has different porosity to the silty soil, those kinds of things, but we often don't know exactly what the value is, especially at the spatial scale that we're working at. So calibration is a process of adjusting those parameter values so that the output is a better match to any observations we have. So of stream flow, maybe we actually measured infiltration with an infiltrometer or something there's different measurements you can use to do calibration of different things with. But that's what calibration is, and we'll come back to it a few times. So that's just what algorithms and variables and parameters are broadly. So then we have these process representation algorithms in our model. So like representing evapotranspiration, for example. And they get done, this gets done in like very lumped ways in some models, and then very physics-based or mechanistic or like broken up ways in other models, and SWAT's somewhere in the middle. But you could have one equation that estimates how much evapotranspiration you'll have for a block of land with a forest on it, as in total, or you can have different equations for each little bit of the process. So like from canopy interception, evapotranspiration from the leaf litter on the ground, the evaporation from the soil moisture, the transpiration from the plants that gets drawn from the soil unsaturated zone, and transpiration from plants that get drawn from groundwater. You could have separate equations for each one of those. And people do try to use experiments to work out what those equations should be and the physics, and build those together into getting what the total ET is. Whereas other models, they have just sort of measured total ET for different areas, and they've come up with simpler equations for the whole block of what's coming out. So that's kind of process algorithms and how they can be broken up into bits. And then you have model time steps. So we also talked about breaking up time into pieces, into steps. And when we make models, you think about like, should we be calculating things for every minute or every hour or every day or every month, like the amount of infiltration or the surface runoff or the groundwater recharge? And the way that decision gets made is usually what data is available. So as we get better and better data, the models everywhere in the world are getting like finer and finer in terms of time steps as well. And then you can think about what is relevant for spatial units and your processes. So like people who are focusing on modeling floods, you tend to look in hours or less because the floods can be fast. But if you're modeling groundwater moves much more slowly. And if you're modeling a catchment as a whole, you have to sort of think about what's the output goal of the whole catchment model and what do you need to get out of it. But we tend to have the limitation of what data is available to drive the model. So if you wanted to model at an hourly scale, you need to have hourly rainfall at a minimum. And so a lot of models are daily. The original SWAT model I worked on is daily. SWAT it can do hourly if we had the data, so that is an option. But generally, like daily is kind of a happy medium for a lot of applications. But as I say, for like very particular flood design work, like a bridge or something, you would want to look at hourly because the bridge could wash away in less than a day. So for now, we're going to work with the daily model. But I just want to flag some things around time steps to be aware of, that when we're representing something at the daily time step, we miss some details of the rainfall intensity and the timing and the response time of the catchment. So if we're using the day as a time step, if the rain all fell in 1 hour, or that same amount of rainfall, like you have 20 mil, or let me give a bigger, let's say you have got a 50 mil rainfall day. If that all fell in an hour, it's going to be quite different than if that was spread out slowly over the whole day. But the model's going to see it and do the calculations as though it was the same. And that's a limitation. It's not going to know the difference between those two when the day is a time step. And then also another issue can be that if a rainstorm happened right around midnight, it can end up getting split into 2 days. So you have 50 mil rain event, but 20 mils of it fell on day 1 and 30 mils of it fell on day 2 because it just happened over midnight. And maybe it happened over the course of 4 hours or something, right at midnight. The model's going to see that as, a 20 mil rainfall day and a 30 mil rainfall day spread over the whole day, those whole 2 days. So the reaction to, and that might have been what happened as well, but they're different things. So that's going to be a limitation in how well, and there's nothing we can do really to fix that. So we just have to understand that that's a problem, and the model's never going to be perfect in its representation of like the flow output it's going to predict. It's going to be limited because we have this daily time step. And the same, like the response of the catchment too, like let's say the rain all fell close to midnight. So you have the rain is on day 1, and the model then might predict that the flow response, if we think the flow response is quite quick, it's going to happen within a day. In the model, you give it rain on day 1, it's also going to have a flow peak on day 1. But maybe the flow peak in reality actually happened on day 2, because in reality, the storm was near midnight on day 1. So then when we compare our modeled outputs to our observed output, we have to realize that that's what happened. So when the model puts the flood peak on day 1 and the observed is on day 2, it doesn't mean that we've modeled it badly necessarily. It's just a limitation of a daily time step. Some older models were monthly as well because they were looking at reservoirs, big reservoirs that, like the storage change and the planning around the water use of a city, you have some buffer because you have this big reservoir storage, and there wasn't good enough data at the daily time step to work with. And there wasn't a computational, like computers were weaker and that sort of stuff. So like models from the 70s. But we like the WRSM model and the SPATSIM models and stuff run on a monthly time step, even though we have better data and faster computers now. But it works for that purpose. but it doesn't work for other purposes. So that's a bit about time steps. Does anybody have any questions about that stuff? We're going to come back to some of these topics, but I just want to pause and check the chat. See anything? Anybody's welcome to jump in and ask something. Again, with these concepts are going to get repeated. I'm just introducing them as like an overview. I feel like, yeah, to get our heads in the right space, and then these things will come up again and again. You'll see how they apply to SWAT in particular, and think about how they'll apply to the data sets you work with and what we should put into the model of the uMngeni and uThukela catchments that are getting modeled. So now I'm going to talk a little bit about, so that leads into, yeah, what we're going to talk about now, which is sort of the modeling project process overview. So I flagged process there because I was using processes to talk about processes like infiltration and recharge and runoff and groundwater flow and that kind of stuff. But now I'm also going to use process to talk about like the project process, and you'll see what I mean now. So when we do a modeling project, we want to define the goals of the project and take stock of what data we've got and what information we have that's not data as well. And then we build the model based on that. And I'll go into these steps now. So developing a conceptual model and selecting then a numerical modeling structure and a modeling tool like SWAT to run with. And then we format our data and we get it into the software and we run our model. And then we can go through a calibration process if we have some observational data to check our model. And we go through a validation process, which is the model performing well enough, like giving us outputs that look reasonable enough that we want to use them for planning. And if not, then we need to go back some steps and try and calibrate more, get more data, that kind of, yeah. So, and then once we get to a stage where we're more or less happy with our model, we can communicate the outputs to decision makers. So some of the goals, so we talked earlier about what some of the initial goals are for this SWAT model, but you guys are all working in different areas, so you can think of more specific ones as well. But as I understood them grossly was looking at point sources versus non-point sources, because that's what we can add quite a bit here. The non-point source stuff is quite hard to measure. And then to look at scenarios of land cover management or land management practices, could be manure fertilizer application changes or all sorts of things like that. But we can talk about what those are more specifically at a later point when we understand what the capabilities of the model are. But there are some ones that have already been identified, which is why we're doing the project. But then once we know what the goals are, we also need to sort of think about, if these are our goals, what are the specific outputs we need to produce? Like how should we be summarizing the data that comes out of the model, like peaks or monthly average flows? And that's the kind of feedback I'll be needing from you guys as well, and then we can work on how do we make a workflow to do that. And then what sort of uncertainty levels are acceptable? Because the model is always going to be uncertain, and we're going to talk about why and how and stuff. But there is always some uncertainty and some level of error, and there's no getting around that. But we have to try and get it into a level that we think is reasonable to use in planning or decision making or forecasting. So then we want to look at our data. So we've got model input data, as we've mentioned before. So we've got rainfall and we've got atmospheric evaporative demand. So that's can be measurements of pan evaporation. So you might have seen some of those. So there's an open water pan and you see how much water evaporates off of it, and you can use that to say something about how much water the plants likely draw and how much would evaporate off of a reservoir. But the other way to do that is using equations that take into account the temperature, the solar radiation, the relative humidity, and the wind speed. And then you need your properties of the catchment area, like size and slope, and the land cover properties, and the soil types and their properties. And we'll get into what those properties are for SWAT, how SWAT looks at those properties later. And then the underlying geology and aquifer properties as well. How much water can it store? How quickly does water move through it? What's connected and what's not connected? And then channel network properties. When is the water in a channel? How do they link? What's getting transferred to where? That kind of stuff. Then we also add the anthropogenic water systems, so external inputs of water withdrawals and transfers, dams, and irrigation practices. And then, so that's all inputs. Some of it's variables, some of it's parameters. So that, yeah, what I said, that variables versus parameters and that kind of stuff, it's kind of they're all lumped into inputs based on some data. And then calibration validation data is observational data on some of the things that the model is actually going to calculate for you. But then you want to use your observations to see if it's calculating it well enough. So some streamflow data. So streamflow data is like the basic. To have some to check if your model's doing well enough. And there are going to be places where we don't have streamflow data. We can estimate, but we can use reservoir storage amounts to check ourselves with. And then what people often do as well, if there's no streamflow data for the particular catchment they're working on, they try and find some nearby that has similar properties and build a model of both together and check that the parameters in that model where there is streamflow data work okay, and then apply the same ones to the catchment that doesn't have. But you're not always able to do that. Then there's other data, if you happen to have it, like if there's any observations of soil moisture, sometimes farmers have probes in the ground for their irrigation systems, sometimes researchers. So I work with SEON, and we put, you guys might know the Cathedral Peak area in the Drakensberg and stuff. They've got lots of soil moisture probes in that area to do hydrology research, groundwater levels from boreholes, actual plant water use data. So there's instruments to do that. That tends to only be researchers. Sometimes agricultural areas can have. So the data that is on things that the model is already calculating, you use that to calibrate and validate how well it's doing the calculations. But a big step in a modeling project is to check the data before we start setting up a model, before we start putting it into the model. Because as I say, garbage in, garbage out. Like if there's big problems with the data, the model is not going to fix that. So you have to look at it first. And it's something that sometimes people don't have enough time to do. They get the data from a source, somebody else prepared the data. The modeler doesn't have time to look at the data. They just use it as is and trust that somebody else error checked it. But it's good practice to have a look at things. So look for unreasonable values, sudden or unexplained jumps in flows or rainfall, like rainfall from one year to the next. I know individual day, you can't really look at an individual day's rainfall and see if it's reasonable or not, but you can look at cumulative. So like this plot here on the right is cumulative rainfall for a few different rainfall gauges that are in the same region. And you see this one just starts jumping crazy in 2010 versus the other three. And they're in the same region. So something funny was happening there. So it could be that the instrument was broken. It could be that there was a gap in the data and somebody patched it poorly or something. So we might just choose not to use that gauge, or we try and fix it somehow. So that goes for any data that we're using. We have to give it a check. For the time series data that's actually driving the model, so the climate data, you generally do need to patch it because it needs a value for every day that you're modeling in a daily model. So if there's a big gap, you have to look at what you're going to do about that. And we'll talk about the rainfall data we'll use for this model another day, but are there nearby places we can patch it with? Are there consistent relationships between stations that we could use to patch with? That's for climate type data or streamflow to some degree for the calibration parts. But for calibration, you don't really need to patch things. You can judge your model against patchy streamflow data, for example, or streamflow data with gaps, I should say. Then you also want to check your data, like what time period is it covering? We like to, ideally in hydrology, we want to model for quite long time periods if we can, because we have dry periods and wet periods, we have El Nino events and all those kinds of things. And you may build a model and check it nicely for a short period of time. And then the climate changes or we go into another El Nino cycle or something. And then you find your model suddenly is really not performing very well. And it would have been better to calibrate it across a period that included some extremes of wets and dries. Because if we built it only looking at a wet period or only looking at a dry period, we might miss some things about the way things work in other climates, other times. And so like the more variable an area is, the longer a time series you need to try and work with in your modeling project to really check that it's working well. And then, yeah, the same thing goes for the streamflow data. And then you need your streamflow data and your climate data, the time periods covered. Same with the water quality to be the same, ideally, if you're going to do calibration. Sorry, I keep going backwards by accident. Then we also want to look at what time period is the land cover data from. And this can be quite important because a lot of like the modeling we're going to do now, the land cover is going to stay the same through the whole model run. So if we're modeling a time series from like 2010 to 2020, for example, and there's a major shift in the land cover over that time, and we hold the land cover the same all the way through, that's going to be something that we're not representing in our model. So we can't expect if there's a big land cover change, there's like a huge one, you can't expect your output of the model to match what we observe in the field if we haven't included that in some way in our model. There are ways in SWAT to have the land cover change over the time period being modeled, but it gets pretty complicated and people often don't do that. So you try and just use the best land cover you can for the time period that you're modeling. But if you're doing a very long one, then you do try and change it in the middle. So we'll come back to that, but it's something to think about when you're looking at your data and what data you're going to use. And then you want to think about how your catchment works before we start getting into like numbers and model structures and stuff. We want to take a step back and say, what do we know about this area? Like which streams flow the whole year round, or are there streams that actually go dry half the year? Or like what do we know about the aquifers? Are there springs? Like are there places where the groundwater is just flowing out and that's where like a stream starts? So those kinds of things. Or like where are big significant wetlands and floodplains? And what do we know about like the depth of the soil over the aquifers and the there's various different aspects of the hydrology that it's good to step back and think about before you dive into putting data into a model. And we have time or not to do that to varying degrees, but it's always a good idea to step back and think about what you know already before you start modeling and make sure your model includes some of that in as best you can. Because you have to make decisions about what land cover types to put in and what stream network to use and that kind of those kinds of issues. So it's great that we have people driving around in the field and walking around in the field and looking at stuff, and then they can come back and say like, this model is not good, because it's not including this. We can't include everything, but if you have an idea of what are some of the big processes happening in a particular area, can try your best. And what needs to be represented specifically to meet the goals of the exercise. So if we want to look at fertilizer applications, and we want to look at fertilizer applications in different kinds of farms, we have to put those farms in like dairy farms or like pasture for dairy, different levels of maize production or something. Like we need to put those in the model as separate HRUs so that we can change them differently when we do scenarios. So we need to step back and think through some of these things before we start building the structure of the model. And also, where do we want our outputs? Because the model will like produce outputs for different sections of a stream. And if you don't break it up into sections, that you want the outputs for, it won't produce an output in the middle of a streamline unless you put a breakpoint there. So we'll get into that. So these are things you want to think through before you even start diving into your software and all of that stuff. Then you select your modeling tool, your software. And in this case, we've already chosen it as to be SWAT Plus, but you want to take into account, you know, how, like, your computing requirements and software licenses and how long does it take to learn and use and stuff. So we'll get into why we picked SWAT momentarily. And then you need to set up and run your model. And then you start processing your data to have it go into the software. And we're going to enter it into the software, and then we run it. And then running a model, we want to test, like, how long does it take to run? Are we getting errors and why? And when you do a model run, you also want to generally do a warm-up period. And the reason for that is that you want to run it for a longer time period than you're actually going to look at the output for. And the reason for that is that, especially for rivers and that you have a big groundwater component, we don't know what the groundwater storage is on day one. And so, like, if we put in too much groundwater on day one compared to what was actually there on day one, that extra groundwater is going to flow out into our river in the model quite quickly, and the flow is going to be too high for a while until it, like, equilibrates. The inputs and the outputs start balancing, and it starts, the groundwater levels start being more what they actually are. And sometimes you have to run the model for like 3 years of time before the outputs start looking reasonable, because our starting day one groundwater storage wasn't right. And it's hard to know what that value should be a lot of the time. And the same with soil moisture in areas where you have a very thick soil layer that stores quite a lot of water, and we don't have a good handle on what the soil moisture was at the beginning. So you run it for a bit of time. The groundwater issue can be quite a big one. So that's why you run it for quite a few years sometimes before the time period that you want to look at to let that balance out. So they call it a warm-up period. So you run your model often with a warm-up period, and then you look at your outputs. A little break for questions there. Don't see anything in the chat. Don't see any hands. I'm going to keep going. So I talked a bit about defining our goals and taking stock of what data we have and doing quality checks and that kind of those steps, and building the model and getting it to run. And that's like a big achievement. It runs and it gives you output and there's no errors and the software doesn't fall apart. And you're like, yes, I have a model. But actually, there's still a lot to do at that point. So calibration and validation and communicating of the outputs, like working out what statistics and things like that people actually want to know, and making a workflow to calculate those and tell people what they are. This is a significant step. So some people, we celebrate a little early sometimes. It's like, it runs and I've got output. It's amazing. We have to really check it. So this step is a bit mathy, and again, a bit, there's a lot of theory and conceptual words and statistics and stuff, but we're going to come back. It's going to come back over and over and over. So if it feels like too much, don't worry. It's going to come, you'll see it in different ways, like practically and more practically later on throughout the training. I just want to introduce some of these ideas to start off with so they can start sinking in. But we have model performance, and that's an assessment you do is like, how well does the model recreate the observation? So stream flow, does it calculate stream flow in a way that matches the observed stream flow fairly well? And there's different statistics that we can look at to do that. And so then you need observed stream flow or estimated stream flow from reservoir water balances to check that for as many places as you can within your modeling area. And then calibration is where, as I mentioned before, is where you go back and you say, okay, like it's producing too much stream flow or too little stream flow, or the peaks are too high and the base flow is too low, or the base flow is too high, like the low flow time periods are too high and the peak flows are too low. And then you need to look at, okay, why would it be doing that? And it's likely, you look back at the rainfall data first, but then if there's nothing obvious wrong with the rainfall data, then you start looking at parameter values to calibrate with, that you can calibrate. So are there things you can adjust about the way what we've assumed about the soils and the land cover that would improve that? And you rerun and you try again. And then validation is similar. You're checking the performance of the model, and this time where you're checking it specifically, like, is it good enough to meet your goals for your modeling project? Like the amount of error, and so there'll be the error in the stream flow, but there can also be error in the water quality, and we'll get to that on a different day, but it's the same concept. So is the performance, is the output compared to the observations good enough to meet to be acceptable for the management applications you want to use it for? And so the process of doing that, is it fit for purpose? How good is it? You have to think, what is it going to be used for, and how much uncertainty is acceptable in the context? And people who work with reservoir management, and some of you might do this, they have a good handle on this generally, of the fact that you have a certain you allow a certain amount of certainty or uncertainty in the amount of water stored in a reservoir to grant a city or a town or other water user an amount that they can use per year, per month, in different seasons and stuff. So they have a good handle on the assurance of supply, if you will. And so what level of uncertainty is acceptable before you can say you can use X amount of water from this reservoir every year, and we're going to guarantee that it can be provided. So that kind of stuff is for reservoir management and water supply allocation. I think it's 98% assurance for domestic, and then like 95 or 90 or something for agricultural water users and those kinds of stuff. So, but a lot of other applications, they don't have, it's a debate sort of how certain do you have to be before you can make a management decision. But I think like flood lines that you guys might work with, and land cover management tends to be a bit more forgiving. It's like, how is it going to make a significant change to our water quality, and what is significant in terms of, I guess, what water quality processing you have to do on your end before you supply it, those kind of things. So, and then like at national scale prioritization, you just want to know, is this area more vulnerable than this area? So you can be less certain about the actual numbers, but you're just trying to say which area is more or less vulnerable, problematic than which other area. So that one you don't have to be so certain. And then there's research purposes. So it really depends on what you want to do with the output. So I've been mentioning error, but I haven't really talked about where the errors and the uncertainties are coming from, but they come from just about every step we've talked about. So there's uncertainty in the measurements, like the rainfall data, the climate data. There's a lot of uncertainty in the property values we assign to land cover and soils. And there's uncertainty in the data because of measurement error, like the instrument had a problem or it didn't work, or a lot of times it's because we are assigning a number to a much larger space than where it was measured. So I measure soil properties in a small pit or a soil core or something, and then I apply it to an entire hill slope. I don't know that one number applies to the entire hill slope or patch of land cover. So a lot of error in the data. Some of it's from measurements, and then there's model error. And that's, so measurement error is when you know how wrong you are. And uncertainty is where you don't really know what the value is, but you actually don't know how far off you are either, because you don't have an observed value for it. And so then you have model error as well because of some of the calculations that it makes on the way are simplified versus reality. So you've got uncertainty and error in your input data, you have it in your modeling structure, how processes are represented, it's a simplification. The parameters are also hard to measure as well, and your calibration data might also have measurement error in it. So you have uncertainty in your modeling outputs. So like this is a graphical representation of that, for example. So we probably won't get to the fancy stage of getting an uncertainty range like this gray band of the output, but we might. We'll see. But it's good to know that even if your model output is this one line, so in this case, the black line is the modeled streamflow, the red is the observed streamflow, and then the gray band is a 95% confidence interval around the model. Like it represents what they thought their uncertainty was. Even if you just have this one line of output, you don't get to the point of calculating that buffer. It's good to know that that buffer exists. Like there's a lot of uncertainty around your modeling output. And then the error is where the red line actually just totally leaves the uncertainty bound. And so that's going to happen and it's going to be uncertain. But we have to just see what is it good enough to do. And they're still generally pretty helpful. And so we measure this with a bunch of statistics. And for the sake of time, I'm not going to go into these statistics today. So I'm going to skip through a couple slides that I have here because we'll come back to it. But there's different statistics you can calculate that give you information on your different things you want to look at. So long-term means, your temporal patterns, your highs and your lows. Oops. I think I somehow got into my slides started advancing by themselves. So generally, there's no single statistic that will give you all the information that you want. So it's good to look at plots as well and to use multiple statistics. And so some models may do well in high flows or low flows, and you need to kind of balance that and what we really want here. So these are a bunch of examples of the statistics. Some people might work with some of these already, like R-squared. Looks at how patterns match. Nash-Sutcliffe looks at how how quantities match, same with percent bias. And we'll talk about these again other days, but just to know there's a bunch of different statistics. It's better to use quite a few of them to give you a more well-rounded picture of how well you're doing on your modeling journey. And then you have to have an idea of what, for each statistic, what constitutes a reasonable value. And there's different ways of coming up with that. So then you look at how well your model is performing against your observed data. And then you can go through a calibration process, which is where you're trying to adjust parameter values to improve your performance, trying to get the stream flow to match the observed or the soil moisture to match the observed, etc. And you decide which parameter values you're going to start playing with and what range of values is reasonable to play with for each one. So just to give examples, it'll be like your soil moisture, your root depth of your vegetation, those kinds of things. And then you need to decide how you're going to evaluate your performance and when you can stop calibrating, like you run out of time or you reach your, oops, sorry, my slides are going by themselves. When you are reaching, you've reached an acceptable limit of error and uncertainty, and your statistics are within your desired range. And then there's manual ways of doing this. You change values and you rerun, or there's automated ways of doing this where you give ranges of values and you let the computer do it and you walk away for a couple days and come back and see what it found. But you need more computing power to do an automated approach for a big model. So then you do this part, and it can be an iterative process of calibrating, checking whether it's meeting your needs, going back, trying again until you get to a point where you think it's good enough to start communicating the outputs to stakeholders. Stakeholders being yourselves as well in this case, it's happening within the organization. So communicating, we need to document everything we're doing. So I've been doing that, and I'll keep telling you guys what's been done. And we can talk about what needs to be modified to improve it. And how you've evaluated whether or not the model is good enough. And then when you start getting into scenarios, how you're accounting for uncertainty when you suggest like this scenario is going to cause a 20% change in runoff or that kind of thing. Like how are we getting that number given the uncertainty? So we'll go back to that other days. And yeah, if the end users, and that's you guys in this case, if you don't trust or understand what's being done, then we've been wasting our time. So you want to keep asking questions and going back and forth here in as much as possible. So some people might have heard this statement in, it gets made, I don't know who said it actually, but I should look that up. But it gets said a lot that all models are wrong and some are useful. So that's true in a way. They're all simplifications of the real world, and there are a lot of uncertainties, as I mentioned, but they are one of the best ways we have to put all of the information we have together about the data and the processes and stuff to get to help us inform management. So it's worth a try, and with careful use, they can really be helpful to put all the information we have into one place and get somewhere from it. But we can't get away from having good field data. It is a common misconception that, well, not a misconception, but people often don't think about it as much. They'll be like, oh, we can just model it. But when you start to dig into all the uncertainties, if you don't have some data to back check, we're making too many assumptions to not actually do some checking against field data, especially when you start thinking about all the different things going on in a catchment. So we really do need good field data in as much as possible to get to predictions we can really use. So before I will break so we're going to start getting into SWAT in more detail now, and how SWAT does these processes and start looking at the software. I'm going to pause for questions. I can see that it's almost 3. So I think if there are any questions, we'll take another 5-minute break so people can run and get something to drink, stretch. How are we doing? Does anybody have any questions so far? Yes, Sivusile. Oh, sorry, Sivusile. Please go for it.
Okay, thank you. Mine is on the accuracy of the models. So I'm just trying to check for somebody who's either a beginner or who's been doing it for quite some time, and you've run your model, you've got your results. Do you have like thresholds in terms of if your accuracy was below or above this level, then you are able to proceed and use the outputs? For example, is it like a 50% threshold to say if ever your results were accurate to this level or below this level, then you're able to proceed, or you need to either remodel or select a different model? Like, is there a threshold that guides whether the results are, you're able to use the results moving forward, or you need to try an alternative?
Yeah, so there's like a whole field. So if you get really academic about it, there's a million papers on exactly this topic. And there's guidelines. It can depend what the application is. So like if you're gonna build a bridge, that might get swept away in a flood, you need to be more careful than if you're just like if you're prioritizing alien vegetation clearing between catchment A and catchment B. Like people aren't going to die with the second example, whereas with the bridge example, people might. So there's different levels of uncertainty and error that you might allow in different cases, but there are some guidelines. These are more like softer things. So for example, there are some guidelines in the literature that we use when it's less sort of exact what you need. And so generally, like if you're in this unsatisfactory category, like you definitely need to go back and rethink. But P bias, for example, is percent bias. And what that means is like on average, how many percent off is each measurement on average, or each, output value on average. So like my stream flow for day 1, my stream flow for day 2, my stream flow for day 3 versus the observed for day 1, day 2, day 3. Like if I look at the average error in those across all the days in my simulation, is it plus minus 5% from the observed? That would be a p-bias of plus minus 5. plus minus 10, you start getting good. If you start getting like, so they generally say sort of like outside of 15%, in your percent bias of your outputs, you are starting to get into a range where you'd want to do more. None of these things are hard and fast though, and it depends on the application. I've seen like often, so that's 15%, suggest 15%. If you're out by more than 15% on the p-bias, that it's generally considered unsatisfactory. I've seen ones that look, say 20%, so some people are more generous. It depends on the application that you want to use the output for. So there's no hard and fast rule for every single case, but there's a lot of suggestions in the literature like these ones. And in other projects I've done, I have picked numbers similar to this and gone for that. And it's a chicken, like the thing is you can keep tinkering with your model forever, but at some point the decision is going to be made whether or not you're finished with your modeling exercise or not, to some degree, like somebody's going to have to allocate the water. So there's also that element. At some point the decision's going to happen whether you're finished or not. So yeah, so there's a mix of things, unless you can delay it, unless you can say like, if you give me another week, I can try and make this better. There is options of delaying decisions up to a point. Does that help? It's not a clean answer, but yeah. But these are good things to start thinking about. Hi, Sanele. Did you want to ask something?
I'm good. I'm trying to mute Usfuisil.
Yeah.
But she's covered, yeah.
Oh, okay. Great. No, thanks for the question. It's a good one. And we'll keep coming back to that because we're going to have to decide at what, like, for the model we're making of these catchments with SWATs. When do you move forward with using the outputs? And it is a tricky one, but there's just guidance in the literature, but at the end of the day, you guys will decide together. So let's take a 5-minute break. Let's come back at 3:05, and we're gonna start playing with the software. Okay, so I'm gonna pause the recording. everyone. Hope we're still okay and we have a little bit of juice left. Gonna start going into, I've started the recording again, and I'm gonna go into some particular stuff about SWAT. I'm aware of the time and I do want to start working on the tutorial, so I'm gonna breeze through, I'm gonna skip a few slides that I have in here and come back to them on another day, but I am going to just flash up some of the concepts quickly, and then definitely by, the next 15 minutes, we'll start opening the software and do a step or two in the tutorial. I did want to cover this stuff, and we'll keep working on that same tutorial next week as well. So not too concerned, but I wanted to make sure people can at least start opening the software and playing around on your own. Okay. So why did we pick SWAT Plus? Modeling software is just code that we use to execute these algorithms and these structures, and they have user interfaces that allow you to build the model, and their user interfaces really vary a lot in their ease of use, and that's a factor. And some of them have multiple options for how you can structure a model, and some of them force you to kind of do it one in a very more specific way. There are loads out there. This is just a brief summary list that I did for another project, but there are loads and loads and loads of models. Every country almost has built their own. South Africa's built a few, like UKZN worked on ACRU, and there's the Pitman model with SPATSIM and WRSM that came out of WITS and others, and then Rhodes University a lot worked on that, various elements of development. And then you might know of many others. So there's loads of them out there, and they all have different pros and cons and slightly different structures. And then they all have these different related, linked modeling elements or types that are linked to hydrology. So hydraulics is like flooding and how much water in channels, like surface water, spreads out over a surface and deals with roughness. And people might know HEC-RAS and HEC-HMS. And then there's very detailed groundwater models that you might use for groundwater contamination spills, or mining uses them a lot. Way more detailed representation of the groundwater. Sediment movement models for erosion, and water quality models. Biogeochemistry, which is a next level of a water quality one. Really looks at like how rocks break down even. And you have vegetation growth and crop yield models and irrigation models and land surface models, as they're called, which sort of have feedback with the atmosphere. So atmospheric and climate models. And then you have models that really focus on water supply systems with allocation rules and economics models. And so you get hydrological modeling software that have different components of these that have been worked in over time. Keep adding it. People are trying to make, the one big great model of everything. And as our computing power allows us and our software coding skills allow us and stuff, people are, getting more, developing things more and more. So you have different software tools that add different parts of this at different levels of complexity into what would have been, or like what started out maybe as just a hydrological model. So SWAT is a soil and water assessment tool, and developed by the US Department of Agriculture initially and Texas A&M University in the United States. It's been ongoing development from models, earlier model that's been going for over 45 years, but it was only started to call it SWAT. It was like they grouped a lot of different models together to make SWAT in the late 90s. As things go, as hydrological models go, it's sort of medium complexity, which is good for computing power, even though we're getting better at that. It can still hang up your computer for a while. Some of you said that you'd used ACRU before in your coursework. The structure and the calculations are quite similar to ACRU, you'll see. And it uses HRUs, and some of the parameters are kind of similar things to what you use with ACRU. But we're using it here because it has an easier interface than ACRU in a lot of ways. It's also freely available, and it's got continued development support through Department of Agriculture, and the US Department of Agriculture. We'll see what's happening with the news, but as far as I know, it's going to continue to be developed and supported there. But it has a large global user base, and people are working on how to make sure it applies in different places. And there's quite a few research groups and consultants and other stuff in South Africa that are using SWAT. So it's looking like it might be becoming more and more of a popular one to use, and it includes elements of water quality and crop growth, which I'll talk about now, and sediment movement that allow us to do water quality with it, and vegetation growth too, which helps with modeling irrigation and fertilizers and that stuff, and that feeds back with the water quality. And because it was developed by Department of Agriculture, they focused on that part as well. So a lot of the routines around that within the model, the way it calculates it, are quite practical and look at things you might want to look at in an agricultural setting. Yeah, so those are reasons why we picked it for use here. Some of you might know that Mike Shee model is being used as well. It's much more for some of the reservoirs, and it's much more computationally intensive. And for a large area like these areas, SWAT can do things more quickly and give us the outputs at the scale that still seems useful. Whereas Mike Shee is gridded, and it takes a lot more time to run, and it gives you a lot more outputs, but you have to balance the factor of the computational time as well. So we've picked SWAT for now for this. But the collection of inputs could be transferred to another modeling tool at other times. So I think everything you learn here is still going to be applicable to other tools too. I'm going to skip questions on that so that we can get through. So a brief intro to how it's structured. As I mentioned, we have the hydrology portion, and then there is some routing through the channel, what they call the water phase processes. So routing through the channel network and routing through also reservoirs and ponds. And there are some water quality calculations that go on within the stream and within the reservoirs as well, in these water phase processes that it does calculations for. And it also has, yeah, nutrient cycling, pesticide modeling, and some erosion modeling to help look at sediment loads in the river. So we'll get to water quality on a different day, but it has these components in it. So let's turn to, I'm going to open up the SWAT website. I'm also going to paste this in the chat so that you can also go there and look around. Sorry, is that right? Site. Here we go. I'll paste this address in the chat so you can also go there. So this website it's got a lot of helpful things in it about SWAT. So it's worthwhile spending some time when you have some time just to poke around in here. I feel like they didn't make some of the menu bars as standouty as one might like. So I just want to show you where some of the things are that you would want to look at. So if you go to software, so SWAT Plus is the newer version of SWAT. SWAT 2012 is the older one, but they're going to keep working with SWAT Plus. And so, yeah, if you go to software, you'll get to this where it has SWAT Plus and SWAT 2012. And you have all these other community tools, and these are things that other users have developed, but you can use, like you can run SWAT models or process things in R. There's other sort of groundwater versions, all sorts of other things here that people, so there's quite a big user community. There's even stuff to interact with it from Python, all sorts of stuff that the user community has developed, and they allow you to put stuff here. So if you go to get started with SWAT Plus, it'll take you to the SWAT Plus particular pages. And hopefully people manage to download and install. And if you haven't yet, try and find someone else who has in the group and work with them. And can catch up later, but definitely by the next time. But if you go on this page, the SWAT Plus page, you get to interface documentation and input, output, and theoretical documentation. There's loads of stuff here that we won't have time to go through all of it, but it's very helpful and it's good for you to know that it's here. So if I go to interface documentation, there is SWAT input and output documentation. There's a Q SWAT manual. So we're going to come to this just now because we're actually going to. Oh, wait, is this the same thing? I think it is. Okay. Yeah, I think this comes with the software. We'll navigate to it elsewhere. The input-output documentation is very helpful. So if we go to the input-output documentation, it tells you about every like input parameter and piece of data that goes in the model. So you'll see all this stuff. Is this alphabetized? No. Okay. So they have like, what's the hydrological well, they don't say, okay, what are the files related to hydrological response units? What are inputs and output? What are the files in the model that are related to soils? And what are the variables in those files? And what do the files look like? There's lots, you'll soon see a lot of models have a lot of abbreviations in them, like PERC, and that's for percolation, and like DP, rooting depth, the total. So there's lots of these abbreviations that'll come up in the model, and all the inputs and outputs for everything can be found on the website. Loads and loads of tables of parameter values. So like BD is bulk density, and then they have, you know, units and default ranges and things like that. Here, I'm not gonna, but just so that you know that it is here for future, and we'll come back to it as well. And so this is SWAT input and output. And if you've managed to reach these pages, and you can also get here in another way, but what I also find really helpful is the theoretical documentation. I'm just going to go back. There's different ways to get to the theoretical documentation as well. So I'll go back and show you that. Going back. So there's also input out. Yeah, okay. So I went through interface documentation. There's also input, output, and theoretical documentation. And then there's also videos about setting up software and installing the software and setting up a model. If I go to input output, okay, this takes you back to, okay, it's all in the same, it all takes you to the same place actually. But what you need to, I think what's not, I didn't find immediately obvious and it took a while to find it, is that the theoretical documentation is in this menu on the left. If you keep scrolling down and down and down, you get to the theoretical documentation. And this is quite handy because this tells you exactly what it's doing for different things. So how is it calculating surface runoff? It gives you the actual equations that it's using for everything that it does. And as I say, you don't need to get into the math necessarily, but we will need to look at what the parameters are that we're putting into the model and what they mean to some degree and where they're involved. So it can help to look at some of this because it shows you what the parameter values mean. And if we get to, like, for example, like how it handles reservoirs, you can go to water routing water bodies, for example. So you can see how it's going to treat a reservoir or a wetland, how it calculates the water balance of a reservoir. So it has all this theoretical documentation that we'll need to, I've read through a lot of this to set it up, obviously, and I'm not expecting everyone to read through everything here, but I just want you to know that it is here. And as we come to things, we'll jump back in here and have a look at what it's doing. And all the equations are here and all the parameters are here, and it's a huge thing. You can get this as a PDF as well for the older versions, but I think for SWAT Plus, they only have it in the website format, but it's quite nice to pop through it that way and you can search. And I hope that if you ask ChatGPT about SWAT stuff, that it comes and looks at this to answer you. Probably. Yeah, so I wanted everybody to know that this is here. And I'm going to skip some of these other bits. But SWAT, as I mentioned, has an HRU structure and a subcatchment. It first breaks things up. First, when you start making a model in SWAT, you delineate a stream network. And then we break that stream network up. It will make a subcatchment every time two streams meet each other automatically. But then we can break it up by additional points. So this picture here, the user for this, whoever made this catchment delineation, they added an additional point here as a point they wanted to get output for. It's not where two streams join. So unless you add a point, it'll make subcatchments every time two streams join. And then you can add additional points where it'll make a subcatchment for. So if you have a monitoring point, or a streamflow gauge or a weir or something, or maybe the outlet of a dam, or so you put a point there and it'll make a separate catchment besides the ones where the streams join each other. And then within that, it breaks things up into HRUs. And then we did talk a little bit about HRU routing. So how HRUs, how these areas of land, when they calculate the runoff for each little area of land, is it added directly to the stream, or does it flow onto another piece of land and then onto the stream, or like flow down a hill slope from the top to the middle to the bottom and then into the stream? And because it's tricky to do that sequence down a hill slope computationally, what SWAT does as a compromise is that you break the catchment area up into upland and floodplain. And then it will take all the HRUs in the upland, and it'll take the runoff from those and then route it onto the HRUs that are in the floodplain area within, or like the low, you can think of it as upland and lowland. And you can delineate that using the topography, and it'll say, okay, these are all upland HRUs. We're going to route them onto the lowland ones, and then from the lowland to the stream. So it's like halfway in between that parallel routing where everything just goes straight to the stream, and that series routing where you go from 1 to 2 to 3 to 4, then into the stream. And so it's like a compromise situation, and you can choose whether you want to do that or not, or you can route everything straight. Everything within a subcatchment goes straight into the stream. So that this is like, and then I think I also mentioned, yeah, that aquifers, the groundwater. In SWAT, you have either one aquifer per subcatchment, or you can have one aquifer for a floodplain and one for the lowland and one aquifer for the upland. So you can choose whether or not you do that. So I'll show you that in a sideways way. So with your basic model structure of SWAT, you have your land surface and your soil, and I mentioned you can do soil 12 layers if you want, but we'll choose how many soil layers we're gonna include in our model. And then it has a shallow, it simplifies the groundwater into one shallow aquifer and one deep aquifer. And this is showing like a hill slope going into a channel. If we show this as, imagine this is one subcatchment. You have these HRUs, the hydrological response units, like this one, the foresty one, this one's a grassland one, and this one's a grassland one right close to the stream, for example. And then they all overlie one shallow aquifer for the subcatchment. So anything that percolates or recharges, like percolates downwards out of HRU1 is going to join the same shallow aquifer as the water that's going down out of HRU 2 and 3. If we choose to separate that, the floodplain area, like an upland and a lowland, of upland and a floodplain, it'll look like this. So for example, so HRU3 is our floodplain one, and it has an associated aquifer. And so you have your upland, which has two different HRUs in this picture, and they both flow, if there's water that percolates out the bottom of them, it ends up in this shallow aquifer, which then flows into the floodplain one, which then flows into the stream. Reasons for doing this, in part, are for water quality modeling, because if we want to look at things like floodplain, like a buffer around the stream, you were able to separate that out, and the fact that the water flows from one to the next and then into the stream, you can actually represent that in the model if you do something like this. Whereas you can't model that very well if everything is routed directly into the stream without like passing over the next one. And so there's a lot of notes on how SWAT is doing the different processes. I'm not going to talk through them today because I want us to actually open the software. These slides are here and I'll come back to them on other days, but it models precipitation. You input precipitation and each HRU gets a precipitation amount based on the input data. So we'll go through the input, how that works. And then irrigation water could also land on the surface. It calculates evaporation and transpiration from the soil and from the plants based on climate inputs, and there's different ways we can input the climate information that's relevant there. And then it'll calculate how much evapotranspiration there actually happens based on how much water is available in the soil and how deep the roots are. And then, oops, to the one circle. Sorry, going backwards. Sorry. End of the day. Okay, hydrology. So surface runoff, and then you have your precipitation. It calculates how much runs off and how much infiltrates using there's a few different options for equations for how to do that. And then the water, either it infiltrates or it runs off the surface, and it'll calculate that for every HRU. Then the water that goes into the soil will get redistributed. It will flow downwards depending on the property of the soil, and it'll flow sideways also depending on the slope and the properties of the soil. And then you can get lateral flow that flows, we call it interflow often. There's different language in SWAT documentation because Americans versus other countries have different words we use for these different processes. And then the water can percolate into the shallow aquifer. SWAT does allow water to move from the shallow aquifer back up into the soil, which we could think of as capillary rise, or it can be the fact that sometimes the roots of the vegetation are really, really deep and they actually reach the shallow aquifer. So it represents that in that way, and they call it revap in the model. And you can decide whether it's allowed and where it's allowed and to what degree it's allowed. Like the water has entered the shallow aquifer, it can get used by the vegetation. And then you have the groundwater outflow from the shallow aquifer into the stream as well. And they call that return flow, which is more of an agricultural way of calling it. Some people call it groundwater runoff or groundwater outflow. And then it also has a deep aquifer. And that's essentially like water that it goes into the groundwater, but then it doesn't interact with the stream within the area that you're modeled. So it's essentially like it's water that leaves the model. And that can happen, but it could be available for pumping, for irrigation potentially, but it doesn't interact in any other way, is that deep aquifer. So we may or may not use that here. And then it does have some modeling of flow through the channels, and it assumes all channels have this basic shape, but it assumes that rivers get bigger and bigger and bigger as you go downstream, but you can modify the actual size of the channels in the model. And it looks at, like, you might have transmission losses through the riverbed or evaporative losses and withdrawals. And then you have these water bodies you can add, like reservoirs, ponds, and wetlands. And they all have different positions in terms of what land can feed them and how their inflows and outflows work. So that was a very brief overview of how SWAT works in particular, and all the nitty-gritty equations for that are in that theoretical documentation that I showed you. And we'll come back again to these things as we start putting parameters in our model. Does anybody have any questions on that before I start opening the software? You good? All right. We're now going to get into opening the software. I want to ask and we've got half an hour. So we'll see how far we get with actually opening it and doing some of the steps in that tutorial. And as I say, we'll come back to it next week as well. So don't stress there. Has have people been able to load QGIS and SWAT Plus on their machines or a machine that they can get to? I want to get a sense of how many people are going to follow along live. Feel free to unmute and just say, oh, people are putting hands up. Okay, cool. Are there people who have not been able to? Not sure. All right, I'm going to keep going, and hopefully some of you can follow along live. I wanted to see if people had particular problems. They could bring them up now in terms of loading stuff, but you can also, yeah, it's trickier to do it over email, but I'll give some time also next week to try and troubleshoot there if I can, if you've had hitches with trying to download and install already. What you get when you install from the website and the email that I sent previously, there's two bits here. Like SWAT has, you build your model structure. So that's like you define your HRUs and your stream reaches and how everything is linked up together in QGIS as a plugin, which is a nice way of doing it for people who have tried some other models. You have to do your GIS work separately and then work out how you're going to get it towards the software, the model. And here it's all tied up into a GIS program, which is nicer. And it also includes in the QGIS plugin some output visualization tools that let you put the outputs back on, like the amount of runoff back onto the shapefile of the HRUs or the subcatchments. Or the stream reaches, which is nice. You can do it in other ways, but it has some tools to help you do that within it. And then there's a second software, which they call the SWAT Plus editor. And we'll see, and so these two, it comes as 2 bits to implement the model. And then so the SWAT Plus editor is actually a separate piece of software, but they talk to one another. And that's where we put in the parameter values. So like the values of soil porosity or land cover types or amounts of irrigation or that kind of stuff. And where we put in our weather data, that happens in the SWAT editor program. And those two, and SWAT editor program allows you to run the model. So that's when it implements all the equations in the sequence that they need to be implemented in, and it saves the outputs as time series files. So I'm going to bring up now the tutorial documents, and I'll show you where you will find it on your side. Let me move my presentation down. Oh. Okay. So I hope you can see, are you guys seeing a Windows Explorer window?
Yes, we can see it.
Okay, cool. And I'm also going to bring, so if you've been able to install SWAT Plus, it should end up in your C drive. I know some people are on different kind of, I don't know how the networked computers are and things like that at uMngeni Water, and if you had to use IT help to install things and all of that stuff. Hopefully it's ended up somewhere on a drive you can find, and it's probably a C drive. But if you can find, it should have created a folder called SWAT. And inside that, there should be a folder called SWAT Plus. Have people been able to find that folder? Let's see. So in that folder, you will find documents. And it has this QSWAT Plus manual. This is also the one that we have. You can also get to it from the SWAT website when you go into SWAT Plus. And if we open this PDF, we're going to follow through here. Oh, that's interesting. Okay. This is, let me I have it open. I'm using two computers here. So one is a server where I have the model running. Let's put this here. So here's the document. And so this is it's a user guide, and it steps you through a tutorial for a watershed. So American lingo, catchment and watershed is the same thing. And so it's for the robot watershed in Ethiopia. But it starts out with some basic stuff about installing and getting SWAT running in QGIS, and how the input data and output data, where things are. And then it steps you through setting up a demo model for which they've prepared the input data and the output data already for you. But what's nice about that too is that you can look at the formats of those files, because those are the formats that I have to use to create the uMngeni and uThukela models, in terms of what the rainfall data input looks like and that kind of stuff. It helps to have that. Being so weird. Sorry about this, technical difficulties. There we go. Okay. Okay. So to start out with, the first step is just to double check you have your SWAT folder, your SWAT Plus folder. The example data sets are here, this robots file. And you'll see it has soils and land use. It has a DEM. It has the climate data. And we'll go through what all of these are. So we'll create something like this for other catchments that we model. And then you want to go ahead and open up QGIS. I'll open up a fresh one. And to get SWAT, the QGIS part of SWAT going, we'll need to if I get to, that's going to be part installation. I think it's actually part of installation. So after you've installed QGIS and you go through all the installation. It's essentially you click yes on installation with the downloads, but then you have to turn on the SWAT Plus plugin in QGIS. Where are the steps for that? They start there. Okay. So I mentioned there's this SWAT Plus editor program that's been installed. And there's the databases of the inputs and the output parameters. And there's this documents folder that I showed you here. And there's a SWAT Plus editor. So I'm sort of going through the tutorial. I'm trying to find, there's the step. Okay. Okay, so this is just telling us about the input and the output data for the example. So I've already mentioned some of that. It's essentially what it's saying in this section is that if you were making your own model rather than using their example, you would want to format your your source data similarly to the way that it's done here in the example data set. But we'll go through that on another day and do it specifically for the uMngeni catchments. And then the structure of the output data. Okay, we'll come back to that. Okay, they started here. Sorry, I thought this step was, for some reason, I forgot this step was put here. So we're going to jump all the way down to step 5, actually, or chapter 5 in this document. And if you have QGIS, you open up QGIS, and we're going to go to the plugins menu, where it says manage and install plugins. I'm going to put my PDF of the tutorial off the screen, but I'm going to keep reading from it and tell you what step, or not reading from it, but tell you where we are in that document. But I think it's taking up too much space on the screen. So you're going to go into your plugins in QGIS, and you go to manage and install plugins. Well, and then it comes up, and because should have gone through all the install already, SWAT plus should be there. You can search. Oh, sorry, that's Q. If you start typing SWAT, it's there, or you go Q SWAT, and it's there. I've already turned it on in mine, but you should go ahead and say install if you haven't, and then it will install. It'll take a few seconds to do that. And once you've installed it, I'm going to close here. Once you've installed it, it will show up here as this S plus box for QSWAT plus. Oh, and then there's another plugin that they say that you need to run QSWAT, actually. That's a standard one, but it may or may not be on or off in your QGIS version. So I'm just going to go back to plugins. And you go manage and install plugins again. They say there's one is processing plugin is checked in the plugins menu. So that's the other thing to check, is it the processing? It's checked. This is a standard part of QGIS to be activated by default. Oh, okay, sorry. It's not there. You see if processing appears as a menu item in the top of the GIS window. Excuse me. Yeah, okay. Processing is there. So you should see this. If not, we would have to go back to there and we'd look for it. Does anybody not have that? Anybody who's following along with their GIS, if anybody doesn't have that processing window and they're struggling to get their SWAT plus, your little SWAT plus to show up here in QGIS, give a shout. So I don't see, nobody's struggling with that part yet. So then the main, once you have this box here, I'm gonna click on it and you're gonna get your QSWAT interface as a plugin within the QGIS, which is a lot like ArcGIS. For those of you who haven't used Q, it's a little more clunky, but it works well and it's free, so that's good. So we're gonna click new project and we'll start a new project. The tutorial guides you, gives some advice about where to put your new project. A concern with SWAT